All right, hi everyone. Because we didn't get to go through all of the calculations that I wanted to do for rockets in class, I've decided that I'm going to film it all instead and just put it up either on Teams or on YouTube for you to be able to view. Okay, so now you can get your data in regards to the rocket calculation on Teams. I made a post about it today. So today is the 22nd of March. I made a post about it, and if you just find the post where it says Sky data, because it was Sky and Bridget who took down the times, you can get your own group's data there. You just have to remember who was in your group. So say the table says Carmen, just remember, like, if I'm Steph, Carmen was in my group, so I'll use the data that says Carmen and take down all of the numbers and make sure you average it. So for each motor, or for at least the first two motor, the A motor and the B motor, every group should have 3 times each for each motor. So you've got to add up your 3 times and divide it by 3 to find the average. And that's just to make sure that the times are fair and they're consistent and they are approximately as accurate as they can. That's why we had to make sure there was 3 different people taking 3 sets of data, so we can average it and make sure it's fair. All right, so we're starting off with the first calculation. You can find a copy of this also on our Teams, labeled as rocket calculations or rocket assessments. If you just go on our Teams, it'll be there. So the first question that we are asked when we look at our assessment is, how fast is the rocket going at launch? So we are looking at the velocity here. And when we look at the velocity, we talk about the rate in change of speed, okay? And something to know about velocity, we've discussed it in class, is velocity is a vector quantity. So we say that it includes magnitude, so things like size, but it also includes the direction, all right? When we start looking at things like velocity, we use this equation here. All right, so the equation that we use is V is equals to, so we use V is equals to, oh goodness. Yeah, so V is equals to U plus AT. Remembering that V equals final velocity. Let me do it on this side. V equals final velocity. U is equal to the initial velocity. A is equal to the acceleration. And when we're talking about velocity, it's the acceleration due to gravity. So acceleration due to G, and T is equal to time. All right? And so the question asks us, how fast is the rocket going at launch? So we're looking for velocity, but we're looking for initial velocity, all right? And we've said that here, that initial velocity is U. So we are looking for U. So in this sense, we have to rearrange the equation. Let me take this off, I'm doing too much. We have to rearrange the equation for U. And once that equation is rearranged, it's U is equals to V take AT. Alright, because now we've looked for U, we've rearranged that equation, they've swapped places, and we've also done the opposite of a plus, which is a negative. What's the word for negative? Subtraction. It's a subtraction, right? So if we fill in all the data that we know here, so when we say that our final velocity, if you were here, we might have been doing the egg drop thing, where we had an egg, which was, what was it above? On a plate, I think, or on a pan or something like that, and we hit the pan and the egg fell into the bowl. But if you did that and you videotaped that, you would have seen at one point where the egg was actually at rest, okay? And we say that that has to do with inertia, the ability to resist motion. So for a millisecond, that egg wasn't moving. And we say the same thing with the rocket as well. Once the rocket shoots off into the sky, before it starts falling due to the downward force of gravity, it experiences 0 acceleration. not acceleration, zero velocity, zero speed change, because it's come to a rest, all right? It's not moving. Just before it starts to fall, it's not moving, okay? So we can say that our final velocity is 0 meters per second, all right? We can also say, let me do this in blue so you can see it a bit better. So our final velocity is 0 meters per second. Our initial velocity is what we are looking for. The acceleration due to gravity is 9.8 meters per second squared, and your time is whatever time you got for your A motor. We're working out the A motor here and dividing it by 3, because you would have gotten 3 times for each motor. All right, my answer, my times divided by 3 is 3.91 seconds. Okay, so we now have to input this all into the equation. So what we're going to do is we are looking for U. Our V is 0, so 0, take, and then our A is 9.8 multiplied by 3.91. Alright, so this is my V, this is my A, and this is my T. Alright, and once you input all of that in, you should get, let me find out what it is. Oh, I didn't do it. Let me check it. Yeah. Oh, there it is. 38.32, because I rounded it to 2 decimal places, meters per second. All right, and that's what our U is. So the rocket at launch is going at a 38.32 meters per second. Okay, that's how fast it's going at launch. All right. Now, this is for my A motor, A83 motor. For each question, you've got to do it 3 times. Once for your A motor, but then you're also going to find it for your B motor. All right, so for B83 motor. Okay, and then you're going to do it again for your C motor. Now, not everyone did end up doing a C motor. If your group did do a C motor, just use the data that you have for your C motor. If your group didn't do a C motor, you are welcome to use someone else's data. Just make sure that you're using, I like everyone to do at least the C3, because we've got 2 sets of data for that C3. So once you get up to doing your C motor calculation for this question here, just use the C63, I believe that it is. Okay, and that should be done. So you'll get your 3 marks, 1 for this, 1 for this, and then 1 for this. Remembering that you have to make sure that you go through and you do it properly. If you mess this section up, you will mess every section up, because these answers will be used in following questions. Okay, so getting this wrong will get the rest wrong, which asks us, what is the maximum altitude of the rocket? So what this question is asking us essentially is, how high does the rocket get up to once the parachute is released before it starts coming back down to Earth? And a lot of you might not have seen this equation before, but we are essentially looking at the position. So the rocket has gone from down on the Earth, on the surface, and it's gone all the way up into the air. So there has been a change in the rate of position. And this is referred to as something called displacement. And displacement is the rate in change of the position of an object. And it's represented by S. So when we were talking about velocity, we usually hand in hand talk about displacement, but just in class we haven't been doing it, we haven't needed to do it, but this is the section here where we will need to do it. And the equation that we use is the equation that goes S, oh, is this working? S is equals to UT plus half of AT squared. All right, so some of you might have seen this equation equation before. Some of you might have not. You might have seen it on the formula sheet, but it's okay if a lot of you haven't seen it before. All right, so what this equation involves is, well, before we rather get into that, let's look into breaking down what they are. So S is referred to as the displacement of the object, and the object that we're talking about right now is our rocket. So S is the displacement. U, like we said last question, is the initial velocity. T is the time. A is still 9.8. And I don't know if I mentioned it when I was doing the last question, but it is negative 9.8 meters per second, or let's say acceleration due to gravity. First, before we get into that, acceleration due to gravity. And I believe that's everything that we need. Yeah. All right, so displacement is the rate in change of position. So if I am standing here and I move to that chair, don't know if you can see it, but I move to that chair, I say that I have moved 2 meters. I have had a displacement of 2 meters. So displacement is measured in meters, right? Our initial velocity is measured in meters per second, and we actually already know what it is because we worked it out for the last question. So my initial velocity is 38.32 meters per second. My time, because I also have rocket data, so my time is 3.91 seconds for the A motor, and our acceleration is negative 9.8 meters per second. Like I was just saying a minute or two ago, I'm not sure if that I explained last question, that the reason it's negative 9.8 meters per second is because we're going up. If we were falling, we would say that we would have our acceleration due to gravity would be 9.8 meters per second squared, because gravity is a downward force. But because we're going against gravity, we are at a negative, right? So it becomes a negative 9.8 meters per second squared. I hope that makes sense, right? And just this half here, what that represents is this whole thing here is essentially being halved. So we're halving the acceleration multiplied by time squared. That's being halved to work out the average. Right, so let's just fill in all our data. So what it's going to end up being is it's going to be S is equal to 38.32 times, I'm just going to put it in brackets so I can kind of separate my numbers so it doesn't look all jumbly, times by time, which is 3.91 plus 1/2. So you can do plus 1/2 or you can do plus 0.5. They mean the same thing. Half of 1 is 0.5. So plus 1/2 times by A, which is negative 9.8, and then times by T, so 3.91 squared. Okay, so if you see here, you will see that we've used time 3 times. So there's a time here and there's 2 times here. All right, so once you input all of that numbers here, you will get, actually, let's just make sure we understand what it is first. So we have our U here. This is what we worked out from our last question. We have our T here. This is my data. You need to use your data. We have the acceleration due to gravity here, and on here we have the time squared. All right, so once we put that into our calculator, if you've got a class pad, it'll help you a lot to use your class pad. That's a big white long calculator, but I've just got my usual scientific calculator. Just make sure you use these brackets here, because you might have the calculator thinking that you are timesing a subtraction rather than a negative. Okay, so the answer to this, I have already done it to save us some time. It's 74.92 meters. Now, I squared this number, I rounded this number to 2 decimal places. All right, So we say that the maximum altitude for our rocket using the A motor, A83 motor, is 74.92 meters. That is the highest it got to before it started coming down. 74.92. Once again, you're going to have to do it again for the B motor. And then you're also going to have to do it again for the C motor. Now, I want everyone to use C3, but if you have your own data, you can use your own data as well. But if you're using other people's data, make sure you keep to one type. So if you're going to use C3 for the first question, use C3 for the second question, for the third question, for the fourth question. If you're going to use C5, use C5 throughout the whole thing so you don't get jumbled up. All right, so we say that that is my answer for our A motor. So the highest it got to using the A motor was 74.92 meters, and you're going to need to work it out again for B motor and for C motor. All right, let's move on to the next question. So this question is pretty straightforward. It's asking us to look at acceleration. Right? And we've worked with acceleration a lot during our classes, so a lot of you will know and recognize and have used this formula many, many times when we say that acceleration is equals to V take U over T. All right, so we say that is our formula here. If we break it down once again, A is equals to whatever by your meters per second. So in this case, actually, we're not referring to the acceleration due to gravity. We're referring to the amount of time it takes for the rocket to go from zero velocity to its max velocity. All right, so how long does it take for it to do that? Because we say that acceleration is the rate in change of speed. So we're looking for what is the maximum amount of time it'll take from the rocket to go from 0 meters per second, because it's not moving at rest, to go to its maximum amount of velocity. So we'll say its final velocity before it starts to fall. Right, so our A would be measured in meters per second. Our V, I sound like a broken record, but it's our final velocity. So final V. Our U is our initial velocity, and our T is equal to time. All right, so once again, going through, we say acceleration is what we're looking for. So that will stay like this. We won't have to rearrange it. Final velocity. Okay, so this is the section where some of you might get confused, because originally we were looking at what's the maximum amount of height that it can reach. And also, what was the first question that we did? How fast it was going at launch, okay? So we looked at the initial velocity at launch. So once it had gone through its inertia, what was that initial velocity? But now, instead of looking for initial, we're looking for final, okay? So we're swapping those results that we got around. And instead of saying V is 0, like we have been using for a while, once the rocket stops moving in the sky before it starts to fall, instead of it being 0, we say, actually, what's that speed? Instead of looking at it being 0, what's that speed? It's a speed, all right? And we say that U instead is now 0, because once that rocket is down there on the surface of the ground, it's not doing anything. It's waiting for something to be done to it, okay? So we say it's at rest. So we say that U is 0, U being our initial velocity. So U is 0 meters per second, but V is now actually 38.32 meters per second. Now you might recognize this number. This is the number I've been using for my U in the last 2 questions, but now it's actually my V. That's the maximum velocity it will reach before it starts to fall, okay? This is initial is 0. That is the velocity it's at when it's on the surface of the Earth. It's not moving. It hasn't blasted off yet. It hasn't launched yet. So it's 0. Okay, so don't get too confused about this part. Just understand that u is 0. Final velocity, the maximum amount of speed it will reach, is 38.32 meters per second. And also, don't get confused with time. So a lot of you might say that my time might be 3.91 seconds, because that's what we've been using for the last 2 questions. But it's actually not 3.91 for this question, all right? Because we say this is the whole work journey. So we say this is the whole flight journey, rather, not work journey. So flight journey, right? But we're not looking for that flight journey, rather. We're looking for the maximum acceleration during launch, not for the whole flight, only during launch, all right? And if you look at the rockets on the manual, you guys might not have seen this or read this. If you look at the manual, it actually tells us that the rocket takes 0.5 seconds to overcome inertia. All right, so we say 0.5 seconds. Okay, and when we talk about inertia, we talk about the ability of an object to resist motion. Okay, so it takes the rocket 0.5 seconds to go from 0 meters per second to 38.32 meters per second. That's how long it takes, 0.5 seconds. Not 3.91, which is the whole flight journey, but 0.5 seconds to overcome inertia, to be in motion, okay? So once I put that all into my equation, so there's my equation there, so we're looking for A. So A is equal to V, so 38.32, take away by 0, dividing it by 0.5, you will get, I've also written it down so I don't have to calculate it and waste time, 76.64 meters per second squared for a 8.3 motor. Right? So that is the maximum amount of acceleration during launch. 76.64 meters per second squared for my A motor. Now go ahead and calculate it for your B motor using your own data, and go ahead and calculate it for your C motor, borrowing from someone's data if you don't have a C motor data. Okay? Relatively simple question, or at least the working out is fairly simple. It's just looking at working out what is the maximum amount of G-force. Now, we haven't really talked a lot about G-force in class, but what G-force is really talking about is what is the force acting on a body due to the acceleration of gravity. And that's what we're going to work out. What is the force acting on the object due to the acceleration of gravity? And to work that out, what you need to do is you need to find your maximum speed, which we have said is, let me use blue, was 38 for me, 38.32. So 38.32, that's maximum amount of speed, meters per second. And you divide that by the time it took to overcome inertia, which is 0.5 seconds, and then you get your maximum amount of acceleration. Now this is what we just did earlier, and the acceleration that we got was 6.64 meters per second. And we've said that that was the maximum amount of acceleration. All right, now with this number, we're now going to divide it by 9.8 meters per second squared, because we're dividing it by 9.8 meters per second squared because that is the acceleration due to gravity. And we're looking at the acceleration of the object, the force acting on the object due to acceleration of gravity, all right? So we go 76.64. This was the answer to my question from part I. So part 3, and divided by 9.8 meters per second squared, and that gives us, or our G force, it gives us 7.82, yep, G's, right? And we say that is the maximum G force experienced by the rocket. 7.82 G's for a 8.3 motor. Right? If you are looking for, say, an actual calculation, what it is the acceleration experienced, and divide that by the acceleration due to gravity. Which is what we did here, or the max acceleration experience, which is what we did here. We took our maximum acceleration experience, 76.64 meters per second, and we divided it by acceleration due to gravity, 9.8 meters per second squared, to get this here. This is what we got. Okay? You will have to do that as well, again, for B motor and C motor. Question is asking us, what is the maximum force experience? And this question, this formula we have seen many, many times, almost as many times as we have seen the acceleration and the velocity formula. And we say that this formula is, none of my pens work. All right, we'll use blue. We say that the formula for force is F is equal to ma. Now, this should be very, very familiar. You should have all have seen, it's okay, you can go fast. You would have all have seen this formula here in class. And we say that F is the force, and it is measured in newtons. Measured in newtons. M is the mass, measured in kilograms. And A is referred to as the acceleration, measured in meters per second squared. Okay, so we are looking for the force, so we don't need to worry about that. Force is what we're looking for. We don't need to rearrange the equation. But it's asking us to look for the mass. And in this case, we are looking at the mass of the rocket. Okay, and I've already calculated the mass of my rocket, and it's 28 grams. However, that's not the full mass of my rocket. I also have to include the mass of the motor, which is, I believe, 16.4, yep, 16.4 grams. And once you add them both together, it comes to 44.4 grams. 44.4 grams. And we say that is the mass of our rocket. However, this is actually where a lot of you get let down in our test. You're not converting. We need to do some conversion here. I've got it in grams, but we need it in kilograms, okay? So we're gonna divide it by 1,000, all right? To get it into kilograms, so 44.4, divide that by 1,000 is equals to 0.0444 kilograms. Okay, now, to make it easier for everyone, I have already weighed out all of your rockets. We didn't have time in class to do it, so I've weighed out all your rockets, and you can find it in the same post as the post that includes all of your data. All right, hopefully that makes sense. So when we look at the acceleration, we recently worked out the acceleration, and our acceleration was, I believe, well, mine was 76.64 meters per second squared. So we've got our mass, and we've got our acceleration, and all we have to do is just input the numbers here. So we would go F is equals to 0.0444 multiplied by 76.64 meters. oh yeah, let's do meters per second squared, kilograms. So F is equals to 3.4 newtons, okay? Let me just quickly pop this into my calculator, make sure it actually is 3.4 newtons, 0.444 multiplied by 76.64. Yep, 3.40. Because we're rounding to 2 decimal places. Kinetic energy, I believe, week 5. We had some kinetic energy homework that used the calculation, and the calculation is KE is equals to 1/2 of mv squared. Now, I don't know if a lot of you can remember back to the homework that we did on kinetic energy. So if this doesn't look familiar to you, I'm still going to break it down. All right. Oh, and when we talk about kinetic energy, we talk about energy that is in motion. So moving energy. All right. So let's break it down. M is your mass. So M is equal to your mass, which is in kg. V is equal to your final velocity. Final velocity measured in meters per second, okay? And half is just referring to dividing that by half, or to find the average, or to times it by a half as well to find that average, okay? So let's input it in. So we will go KE, different color. We would go KE is equals to 1/2 times the mass. Now we will use that same mass that we used last question, which what was it? Oh yeah, 0.044 so times 0.0444, and then multiply that by 38.32 squaring it, okay? And this is from my first initial equation when it looked at the max velocity. All right, and when we input that into our calculator, we should get, let me do it right now, 0.5 times it by 0.0444 times it by 38.32 squared. So I got 32.60. Well, it was 32.598, but just rounding it up to 2 decimal places is equals to 32.60. And because it's kinetic energy, we measured that in joules. All right, final question of the booklet. It asks us, what is the maximum potential energy of your rocket? And we did potential energy at the same time as we did kinetic energy, and we said potential energy is the energy that is stored. All right, and the equation that we use to discuss potential energy is PE is EP is equals to mgh, and that's the equation we use to work out potential energy. All right, so we say that m is equal to the mass, g is equal to gravity, acceleration due to gravity, and h is equal to height. Okay? Now, when we're talking about the mass due to the maximum potential energy, well, actually, first off, let's say at maximum potential energy, we're saying it's at the highest, at the peak of its height. All right? So we say once it's reached the highest that it will reach, what is its maximum potential energy before it starts to fall, essentially, before it starts to move at a downwards force. Now, our mass wouldn't be the same as the mass that we've been using. And the mass we've been using is the 44.4 grams, or also the 0.0444 kilograms, okay? It wouldn't be the same. And the reason we say that it's not the same is just similar to a real rocket blasting off into space, something that the rocket needs is fuel, okay? And it burns that fuel to be able to launch itself up, bring itself up into that space to overturn the gravity. It uses up its fuel. And similar to our rocket, we say that we've used up some of our propellant, okay? And some of our mass is made up of the motor, is made up of 10% propellant, okay? And at the height of its flight, at its apogee, I hope I'm saying that right, at its maximum altitude, it's burnt all of its propellant. So 10% of it is gone, okay? So if we use the percentage, the mass of just the motor, which is 16.4, if we go 16.4, so if we say 16.4, all right, and we multiply that by 0.9, and multiplying it by 0.9 will take away that 10%, we will get, let me work it out, 16.4 multiplied by 0.9, it gives us 14.76, okay? So once all the propellant has been burned from the A motor, it weighs 14.76 grams, okay? That's how much just the motor weighs. So mass of a motor. Mass of A83 motor. All right, but that's not our full mass. We actually have to include the mass of the rocket. And my mass of my rocket was 28 grams. All right, so we go 14.76 plus 28 grams, and that gives us 42.76 grams. Remembering that mass is measured in kilograms, so we've got to divide it by 1,000. So dividing that by 1,000, we'll move those decimal places across. Let's do it for 76 divided by 1,000. Yep, it moves us 2 across, so is equal to 0.04 276 kilograms. All right, and we're going to use the whole thing. Let's use the whole thing for our mass. And that is our mass. Okay? Now, we're seeing that gravity is still 9.8 meters per second. Just making sure I'm following along. Yep, we say that gravity is still 9.8 meters per second, but it is a negative because we're still flying. All right. So 9.8 meters per second, but it's a negative because we're going up instead of going to the downward force. And what else do we need to work out? Height. Now, we can use that height from the question that we used earlier. I believe it was question 2 or question II. And I've written it down here so I wouldn't forget. Our height is 74.92 meters. All right, so at its maximum potential energy, the height is 74.92 meters, okay? So we've got height here, we've got gravity here, and we have got mass here. So if we input all of those numbers, it'll be EP is equals to 0.04276 multiplied by negative 9.8 multiplied by, let's put these all in brackets actually, multiplied by 74.92 meters. All right, and that will give us our potential energy. So if I pop that into my calculator now, 0.04276 times it by negative 9.8 meters per second squared, times that by 74.92, and that gives me a negative 31 point, let's go 40, because I'm rounding up joules. And that is our maximum potential energy. negative 31.40 joules. Make sure you're also doing this for your B motor. So this is for the A83 motor. So you'll need to do it for the B motor, okay? Now, the B motor mass will also change, okay? The B motor, so this is the motor mass. Oh, sorry, wrong one. This is the motor mass for the A motor. Just giving you a bit of an example, okay? This is the A motor mass, right? It'll change once you work this all out because the B motor mass is actually 20.2, I believe, grams, okay? Or roughly off of that. I have written it all off on the Sky data document, just off the top of my head. I can't remember the precise one, but I believe it's 20.2 grams, okay? And you're going to need to times that by 0.9%, right? And you're going to need to add that to whatever your rocket weighs, okay? So your mass will be different. You have to make sure you understand that. Your C motor mass will also be different. I can't remember what it is off of the top of my head. But when you go to work that all out, you have to make sure you're using the mass of your B motor, not of just your A motor, to work out what the potential energy is for the B motor, using the rocket with the B motor. Does that make sense? Hopefully that makes sense. So make sure you're using the right mass, right? And it'll be all, you can find that all on our teams. And that is it. We are done. Just thinking of if there's anything I have missed. No, I think that's it. Just remembering to make sure that you are calculating 3 different motors for each question, okay? Using the right data for each question, using that motor mass that will change for each motor, okay? Hopefully this has helped you. I'm sorry we didn't have time in class. We're running out of time to do things, so I think we have to do some of it for homework. So hopefully this will help you through. All right, good luck everyone. It's all listed here. Use your whole booklet, so work through things like your hypothesis, your conclusion, your evaluation, do your results, do a results table, do your variables. So go over your independent variable, your dependent variable, your control variable. You will have to do your aims, your title. All right, all of that is in your booklet. If you can't find the actual booklet, I have attached it to Teams, so check our posts. I post everything in our posts. But apart from that, and you can do it on paper. As long as you're saying what question is what, you can do it on just blank pieces of paper. All right, good luck everyone.